Thank you so much. My name is Fnadi. I am a PhD candidate at Institut des Systèmes Intelligents et de Robotique at Sorbonne University. So today I am so happy to introduce you one of my research topics titled Predictive Control with Obstacle Avoidance on Slippery Grounds for Off-Road Mobile Robot. So I am interested in my PhD to this kind of mobile robot who can move in off-road context to accomplish some missions and some tasks as agriculture, military, and protection, civil protection. This kind of mobile robots are subjected to some constraints related mainly to the environment because they have to move at high velocity to reduce the time of intervention. Also, the environment is unknown, and there are some variability, high variability of the environment, mainly the contact between the tire and the ground. So we have to master this contact. Also, there are high mechanical solicitations and dynamic solicitations that we have to master that can generate some problems of stability and sometimes the risk of the tip over of the robot. So the problematic that I'm interested in this work is I will focus mainly for off-road mobile robots moving at high velocities, and we have to estimate in real time the environment and the slippage parameters, taking into account the dynamics of these vehicles. This is the global scheme of my work. So here we have, So here we have the mobile robot, off-road mobile robot who moves in off-road context. The environment is unknown and variable. And the first block that we are interested is the control, the vehicle control. So here we propose some new approaches and some new strategies to ensure the high stability of this vehicle. So we propose a new model predictive control that takes into account the cost function that we have to minimize, taking into account the vehicle dynamics, also the prediction in the future, to ensure the path tracking. So we have a reference path is the first block there, where the path is defined by the GPS data, and the robot must follow this path at high velocities. And also we have to respect some constraints, mainly the sliding and steering constraints. The second block, we have to estimate in real time and observe in real time some ground parameters, mainly the cornering stiffnesses and the friction, in order to enhance the path tracking task and the control of the vehicle. And the last part, I'm interested also to the high-level controllers, mainly the obstacle detections using some sensors as LiDAR, 3D, and also we are interested to obstacle avoidance by proposing some new strategies to avoid efficiently detected obstacle in the environment. This is the experimental platform that we use, that we have designed. It's a double steering off-road mobile robot. So we have two Ackermann systems, and we have also two Ackermann systems in order to steer the front and rear. So the mechanical design is very complex. And we have also for suspension, for passive suspension, in order to increase the stability of the vehicle according to the environment. And we have also some embedded sensors, mainly the GPS RTK. We have IMU to get the localization in real time, as well as the orientation of the vehicle in the environment. And we have also the LiDAR 3D in order to perceive the environment and detect obstacles around the vehicle. So this work is one of the works of my colleagues. It's one of the PhDs that was defined in 2012. He controls the roll of the vehicle. So we have two active anti-roll bars to control the roll of the vehicle and prevent the tip over of the vehicle in the high curvatures. I will talk firstly about the dynamic model, mainly the interaction between the tire and the ground. So here, the difficulty of the modeling is mainly the characterizations of the contact forces. So we can define firstly the side slip angle is the angle between the speed of the center of the wheel according to the plan of the wheel. So in the literature, we can find a big number of models that can allows us to express these forces according to the sliding angles. So in this in this kind of model, we can distinguish two parts. We have the linear part, or the linear zone, where the forces, the lateral forces, vary linearly according to the slip angles, and we can express the linearity coefficient denoted CF and CR. They are the cornering stiffnesses that are which depends mainly on the properties of the tire and also the adhesion conditions. So these parameters needs to be estimated in real time in order to be injected in the vehicle control in order to enhance the performances of the tracking. And then we have the skidding zone, is the non-linear part where the vehicle is not controllable. So we want to keep all the time the pseudo-sliding area and the linear area where the vehicle stay controllable. So for the vehicle dynamics, so here we use a bicycle model and bicycle model because our vehicle is symmetric according to the vertical plan, and also we take into account the geometry parameters, mainly the side slip, mainly the slope angle. It's the inclination of the vehicle according to the lateral axis, and the bank angle. The bank angle is the inclination of the vehicle according to the longitudinal axis. So my presentation will be divided in three parts. In the first part, I will talk fastly about some results according to concerning the constrained MPC based on the dynamics. And the second part is the tire-ground interaction estimation. And the last part, I will talk about the high-level controller in order to perceive and avoid detected obstacles. So I will focus in this first part, in the first block. So here I will focus about the control block. We have to express the cost function that allows the path tracking task, taking into account the dynamic and the predictive approach. And also we have to express all the constraints, mainly the sliding and steering constraints. So here we have proposed a new formulation of these constraints, as well as a new formulation of a new quadratic programming that takes into account this cost function to compute the optimal and dynamically consistent front and rear steering angles of the vehicle. So I will talk firstly about the concept of the MPC. The MPC, we have the reference path, the reference trajectory that we have to follow, and we have the horizon, prediction horizon. So we have to project the predicted output that we calculate according to the dynamic vehicle. We can project this predicted output, and we have to minimize the error between the reference trajectory and the predicted output along the horizon prediction. So the purpose here is to optimize this quadratic programming. So here we optimize the cost function that minimize the reference trajectory according to the predicted output, as well as the variation of the control of the sequence of control of inputs. And we have to respect some constraints, mainly the steering angles limits and also the speed of steering angles in order to ensure the stability and prevent wide variation of the steering angles. And we have also to respect the pseudo-sliding area bounds because we have to stay in the pseudo-sliding zone where the vehicles stay controllable. So we did some validation of this MPC, constraint MPC, in the first time by simulation using ROS-Gazebo. So here we can, as can clearly be seen from two scenarios. So we have chosen two reference paths, the Z path and the O path, and we can see that this constraint MPC allows the robot to follow successfully the desired path by calculating at each time step the optimal front and rear steering angles. Here we can see some good results about the first scenario. So here we have the Z path, and it can be noticed that the lateral deviations becomes much important at high curvatures because of the high lateral acceleration, which is proportional to the curvature of the path. And another good result is we have the steering angles and side slip angles. They are all the time kept between the bounds of the constraints. which is important for the security and the stability of the vehicle. Furthermore, we can see for the first curve that at low velocities, it's the blue one. At low velocities, the front and rear steering angles are symmetric, and at high velocities, the symmetry is broken because of the sliding parameters. Also, we can see that once the constants of side slip angles are achieved, the lateral error becomes much more important. We did some experimental results using the real off-road mobile robot, and we choose a high curvature path, reference path, and we can notice the same results than the simulation part. For the second part, so the purpose of this part is to improve the path tracking task, which is based on the vehicle dynamics. So the vehicle dynamics is related to some parameters, mainly the tire cornering stiffnesses, and also the geometry parameters. So these parameters need to be estimated in real time in order to be injected at each time step in the controller in order to enhance its efficiency. So I will talk fastly about these observers that we have proposed, and I am available if you want more details about these observers. So this is the first observer. It aims to observe and estimate the front and rear tire cornering stiffnesses. We use here nonlinear approaches that mix between the steering angles as well as the lateral velocity and angular velocity to have to estimate in real time these coefficients, and then will be injected in the constraint MPC to enhance its efficiency. The second observer aims to estimate the road bank angle and the road grid angle. So here we use a linear observer that makes use of IMU sensors, mainly the accelerometer and the gyrometer, to estimate at each time step these angles, and then to compensate the gravity components in the constraint MPC. This is some results about this part using the simulation validation. So here we can see that according to the nonlinear observer that we propose, we can estimate in real time the front and rear steering angles that converge to the same value. For more details and to show good figures, here we choose different initial conditions for the cornering stiffnesses, and it can be noticed that this cornering stiffness converge to the same value that represents the real cornering stiffnesses of the environment of the gazebo environment. And also we did some simulations using some inclined environment, and we can estimate also the inclination of the vehicle according to the environment. Another good result is the lateral error. The lateral error, it can be defined as the distance between the center of mass of the vehicle and the nearest point of the reference path. So it can be noticed. So here we have three scenarios. The first scenario in green curve is without observation. And once we integrate the nonlinear observation, the lateral error improves 3 times. And then when we integrate the geometry angle observer, we improve much better the lateral error. The same thing for the side slip angles. We have an improvement of 2 when we estimate in real time the cornering stiffnesses and lateral and geometry parameters. So in conclusion, we can see that estimation of the environment parameters in real time can improve highly the accuracy of the path tracking as well as the lateral stability of the vehicle. So we did also some experimental results to validate our observers, and we guessed the same results. The lateral errors becomes smaller 2 times when the observers are not used, as well as the side slip angles becomes also smaller. The last part will focus mainly. So we want that our robot will become much autonomous. So we have to integrate also the high-level controller. The high-level controller aims to ensure the obstacle detection task as well as the obstacle avoidance task. So obstacle detection task, we have used a LiDAR 3D in order to perceive the environment in real time. And for the obstacle detection, I will explain you firstly the strategy that we have used. So we have the reference path that the robot must follow, and we have the safety distance. So the safety distance is denoted DS, is the distance which is expressed as the square of the velocity and lateral acceleration of the vehicle. So once an obstacle is detected near of the global reference path, we have to determine some significant waypoints that allows the robot to prevent efficiently this obstacle. And then once the significant waypoints are selected, we have to select some control points between each two set points, and then we have to these control points have to be chosen such as the continuity with the global reference path are ensured. And then we generate a set of Bézier curves for each section, and then for each section. So the question that I can ask you how we can select the best Bézier curve for each part. Any answer? So the criteria that we have adopted is this one. So we want to minimize the curvature of each Bézier curve. So we have two constraints to respect. We have the kinematic constraint is the first constraint there, which depends on the maximum steering angles of the vehicle, and we have the second constant is related to the contact conditions. It's related to the friction conditions. So we have kinematic and dynamic constraints. So the curvature must be chosen such as it can be achieved by the vehicle kinematically and dynamically. And then we have to minimize this curvature. The minimum curvature, it will correspond to the path that the vehicle will follow using the MPC constraint MPC. For the validation of the detection part, I will talk firstly about this because we use PCL, some filters in PCL. So we get the point cloud given by the LiDAR 3D, and we make some processing of this point cloud, and we generate some clusters, and we can know the distance between each cluster and the vehicle, and we can manage the things. If the distance is less than the safety distance, we can apply this algorithm. So we validate first our algorithm using the simulation results. So we have the reference path here, and then we put some obstacles in the global reference path. And our strategy must to allow the robot to generate the avoided path using two Bézier curves. So we can notice that our strategy works very well, but we have sometimes some important lateral error and angular error along the local reference path. We did also some experiments for this strategy, and we can notice the same results than the simulation part. To conclude, in this presentation, we have proposed a new strategy for the path tracking task using a constraint MPC. The main contribution of this part is we have proposed this problem as a quadratic programming that includes some constraints, mainly the sliding and steering constraints. The second part, we have proposed some estimation, some environment parameters estimation in order to enhance the efficiency of these path tracking controllers, which depends on the vehicle dynamics that is related to these parameters. In the last part, we have proposed a high-level strategy that aims to detect obstacles and propose some approaches to avoid them efficiently and fastly in real time. As the future works, we aim to improve our detection algorithm without using the PCL library, which leads to a high computation time. And then we want to propose a new QP using the whole body dynamics that includes the longitudinal, the lateral dynamics, and the roll dynamics. Thank you very much for your attention.
We won't have so much time to ask a question, but if you have a detailed question, you can go in Paris Friday, because I think that Mohamed will defend his thesis. And Friday at Isir, at what time?
Afternoon.
In the afternoon. Yes, so if you have transportations, and or if you live in Paris.
Yes, you are welcome.
You're welcome. But
Yes.
we have time to take short questions while Laurent is preparing. Okay, so short question? No, just to mention. Do you have the possibility to take into account some more constraints in the predictive control? You take stability, you take accuracy of tracking. Can you also take some other constraints?
Yes, normally this is the outlook that we want to do, to enlarge a little bit our quadratic programming by adding some energy in the cost function and also some other constraints maybe related to the stability or controllability of the vehicle, as well as some other constraints related to the role of the vehicle. Maybe we can limit the role between two bounds in order to enhance much more the stability of the vehicle.
Okay, so good luck for your PhD and thanks again.
Thank you so much.